In this work, we address the high computational cost of evaluating signed distance functions by introducing a set of optimizations specifically designed for construction trees, enabling faster and more efficient rendering and modeling of implicit surfaces. Implicit surfaces from construction trees are well suited for complex geometry but expensive to evaluate, especially for rendering and ray tracing. Standard acceleration structures can't be used without breaking signed distance guarantees. We address this with new node types that preserve the distance property even in unbounded regions. Combined with proxy nodes, continuous load, and normal warping, our method cuts evaluation cost while keeping accuracy and remains compatible with existing optimizations, offering major performance gains. To significantly reduce the cost of evaluating complex signed distance fields, we introduce 3 complementary techniques: proxy nodes to skip evaluations far from the surface, continuous proxy nodes to smoothly blend between exact and simplified fields, and level of detail nodes to adaptively switch between high and low resolution representations based on the viewer's distance. Proxy nodes help accelerate signed distance function evaluations. At the center, we have the boundary of an implicit object. Around it, we define a proxy region that encloses the object with a small margin. Inside this region, we compute the exact value of the field, just like in a standard evaluation. But for points outside, instead of evaluating the full field, we return a simplified estimate based on the distance to the proxy boundary plus a small offset. Continuous proxy nodes allow us to reduce computation while maintaining a smooth and accurate field. Near the surface of the object, we keep high precision to preserve detail. As we move farther away, we gradually blend between the exact field and a simplified version. This transition happens smoothly over a defined region, shown here as a gray band around the object. The idea is to avoid expensive evaluations where high precision isn't needed, but without creating any sharp discontinuities. So instead of switching from one function to another, we interpolate between them in a way that's both safe and efficient. Level of detail node reduces computation by switching object versions based on viewer distance. We use 2 subtrees here, one representing a high-resolution version of the object, and another a simplified, low-resolution version. When the evaluation point is close to the camera, we evaluate the high-resolution subtree to preserve detail. But as the point gets farther away, we smoothly transition to the low-resolution version. This blending is done by interpolating between the 2 representations, ensuring continuity. Now I will explain the modification of the construction tree with the addition of our new nodes. First, we start with an unoptimized tree. Then, we present the results using levels of detail, which simplify the evaluation of the noise function. The second example demonstrates the use of a proxy, which limits the evaluation to the area around the object. Finally, we show an optimization that combines both proxy and load nodes, resulting in an acceleration of nearly 20 times compared to the initial scene. Here, we present several examples of objects along with the results of using proxy nodes and levels of detail. A manufactured pipeline scene was created. We constructed subtrees of pipelines, which were then combined through unions to obtain a complete scene consisting of 174,000 primitives. By using loads and proxies, we achieve a speed-up factor of 400. Some complex scenes do not need to be visualized in their entirety, and the use of levels of detail is an effective way to reduce computational costs. We illustrate this with an example of a train carriage, first shown without any levels of detail. Next, we apply a single level of detail with a smooth transition zone. Finally, we introduce 2 levels of detail, allowing us to further reduce computation time. Depending on certain operators, care must be taken when using proxies. For example, in this case, the proxy node introduces a discontinuity on the surface when combined with noise. To resolve this issue, the use of a continuous proxy is required. To conclude, we present the result of a complete scene containing around 5,000 nodes. Although adding nodes increases the complexity of the construction tree, we achieve a significant speedup, especially on GPU of up to 400 times faster. Thank you for watching.